Hello and welcome everyone. My name is Masoom Hussain and I will be delivering this tutorial on ADC DSP based high-speed link design. First, a little bit about myself. I finished my bachelor in 2002. Then I finished my PhD from University of Toronto in 2010. Between 2008 to 13, I worked on various industries on high-speed link design. I returned to academia in 2013, stayed with University of Alberta for 10 years, and very recently I have moved to Carleton University in Ottawa. So, the motivation for studies can be well understood from public transport point of view. Imagine all these people needs to move from this place to another. If each of them were using their own individual car, I would need many more lanes on this highway. Instead, if I put each of them in their designated seat in the bus, I can move them from one place to another, but I would not need those lanes. Not just that, I would save a lot of fuel, and most importantly, I will reduce my carbon footprint, which really matters in today's context. Similar scenario happens when I try to send information from one chip to another. We can think of these interconnect between them as my information highway. As according to Moore's law, the dimension of the chip die size is reducing, and so is the peripheral area. So now I can fit less number of links. Therefore, I need to send more information through them. The technique that we adopt is known as time division multiplexing, where each of these information stream is mapped to a unit interval that is also known as bit period. After serializing this data, we send it on the other end, where first bit decision is made and then deserialized to their designated destination. Therefore, this serialization and deserialization in shortened form is known as SerDes. Note that as we are serializing more and more information, and this bit period is going to increase, is reduced, and the data speed is going to increase. So, if we look at historically, such approach has been adopted from early 1980s. When we were first installing fiber network, due to cost, the same fiber was used to send more and more bit stream as shown in here through these multiplexers. Then it has been adopted in many electronic devices. Most recent adoption is probably these high-end cars where we have many sensor nodes all over the periphery of the car, but the central display requires to display them. Therefore, we need to serialize video, audio, and other data streams. Now that we understood the motivation and the scope of SerDes, let's dive into the detail. Here is how we have organized it. First, we will cover the motivation, not for SerDes, but why they are moving to ADC DSP based implementation. Then the necessary background such as ISI, equalization, timing recovery, jitter, etc. Then we'll see how these techniques evolve to the digital domain, associated challenges, and what can we do to overcome them. Now, let's start with a recent trend. So, on the x-axis, I'm plotting last 20 years reported data rates in terms of their speed. Obviously, the internet traffic, data center demand suggests that there will be an exponential increase in the data rate for the reported links. But we are more interested knowing the architectures they are adopted. That's why they are categorized into ADC DSP based with the green boxes. And as we can see, the highest data rates that are reported in recent 4-5 years are all adopting ADC DSP solution. Similar trend can be observed in terms of technology nodes. Note that the latest technology nodes are really the smaller dimension, therefore concentrated on this side of the chart. And in these technology nodes, also the highest reported data rates are also adopting ADC DSP solution. To summarize them, what we can say is that at high data rate, 50 gigabit or higher, the links that are implemented in 10 nanometer or lower technology nodes, those are adopting ADC DSP based solutions. In this tutorial, we will try to understand what is the motivation behind that. So we can start with what happens when we try to send a high frequency information or high speed data through a lossy channel. So let's start with the channel characteristics. Here is the frequency response of the channel, and as you can see, it has a frequency dependent loss. In fact, if we try to send 10 gigabit per second data, we have to compensate about 10 dB loss at 5 gigahertz. Now first we understand what this loss does to the transmitted bit stream. An intuitive way to understand that is to send a single bit response 00100 stream that is generated by serializing lower data streams. Here zeros are represented with 0 and 1 is represented with VDD, which happens to be about 900 millivolt supply. This pulse due to frequency dependent loss is going to get dispersed on the receiver side. The first few things that we observe here is that the pulse amplitude is reduced, and then these sharp transitions has disappeared. But most important impact is that this one has spread such that some of its residue appears before that, as we see through the elevation from the level 0, and some of it spreads to the next one through similar elevation from the 0. So these two components are known as precursor and post-cursor ISI, and these components are known as inter-symbol interference, as one symbol's information is spreading over on both sides. To understand the ISI impact, consider a very simple scenario of 2-tap. Here the current symbol's response is represented with H0 and its residue is represented with H1, which happens to be the first post cursor. So at any received sample, I will see the combination of my current transmitted bit and also the previous transmitted bit. Since these two bits can combine in 4 possible ways, they translate to these 4 levels, which we will refer to as constellation points. When both of them are 1, then H0 and H1 will combine in a constructive manner. But when one is 1, the other is 0, then we see H0 minus H1 reflecting this constellation point. Similarly, other 2 constellation points can also be mapped. The first thing that comes to mind, in the presence of H1, we see the distance between 2 constellation points has reduced. That means when the bit decision will be made, I will have less margin. It is not just the voltage margin reduction. When we construct a transition from one symbol to the next symbol, we see that the zero crossings, rather than being in one distinct position, they are spreading over, and this is known as data dependent jitter. These two factors can be combined into something called I diagram, where we send a random bit stream from the transmitter side, and after convolving we get this I diagram, which means we have folded over a single UI. We still see these two distinct points, but on top of them I have crosstalk and other noises that creates this noise plus ISI PDF. Similar distribution also happens at the zero crossing. We have these two distinct peaks, and on top we have other noise that creates this PDF. Extending this PDF, we can actually extrapolate and find out what is the achievable PER in such scenario. In a practical channel though, there will be many more ISI components. So when we send a random bit stream from the transmitter side, we receive a input data streams where the level of 1 can be significantly dropped and the level of 0 can be significantly elevated. All these factors can be well captured when I fold them over a single UI to generate an I diagram. As you can see here, the level 1 has actually spread out, and due to many noises, it has smeared out rather than creating distinct levels. And the similar thing happens for 0. Overall, the eye opening has significantly dropped in the presence of ISI. However, the ISI is still not so severe. Therefore, in this case, once we extend these noise PDFs, we can see that a reasonable BER is still achievable. Now let's shift our focus on the receiver side on the bit detection. Ideally, we would like to sample at a location where the error probability would be minimum, meaning the received signal should be furthest away from decision threshold, and that happens to be the middle of the eye. Note that this eye is not going to be static. Due to unavoidable jitter on the transmit clock, this eye will be drifting over time, and that drift must be sensed at the receiver side. Therefore, slope is where it is highest is the right location to sense such a drift, and that happens to be the edge of the eye. Usually, the CDR is the one that tracks such a drift. The purpose of the clock and data recovery, or CDR, is to recover a clock from the input eye such that its sampling point happens to be the middle of the eye, or where my bit error probability is at its minimum or the SNR is at its maximum. Not just that, any drift in the input eye should be tracked such that this optimal sampling point is maintained. From jitter viewpoint, CDR looks like a low-pass filter, meaning if the incoming eye is drifting at a relatively slow rate, meaning the zero crossings are varying slowly such that we are well within the CDR's tracking bandwidth, then it will recover a clock where it will synchronously dither with the input eye, meaning the red input eye will be sampled by the red clock and green input eye will be sampled by the green clock. Because in both cases it maintains the optimal sampling point, there is no loss of relative timing margin. In such scenario, we can tolerate significant amount of jitter. However, as this jitter frequency is increased, we are outside its tracking bandwidth. Therefore, the CDR won't track the input jitter and it will be parked at the middle of the eye. Therefore, I can tolerate only half UI of jitter in this case. Since some amount of jitter must be present in the transmit clock, the link has to still remain error-free. To accommodate that, in most of wireline standards, there is a jitter tolerance mask that is, for example, shown with this red dotted line. Its relationship to the tracking bandwidth is illustrated here. Note that within the tracking bandwidth, it can tolerate significant amount of jitter. But outside this tracking bandwidth, tolerance drops to 0.5. Therefore, if the tracking bandwidth is relatively low, then there is a possibility that we would be violating the jitter tolerance mask. Therefore, the tracking bandwidth should be increased. In fact, it seems like increasing the tracking bandwidth is a simple way of improving jitter tolerance. But this should be considered with latency. In the presence of latency, trying to increase the tracking bandwidth will cause peaking. Because my recovered clock has more jitter than the input data stream, we will see a dip in the jitter tolerance plot that will violate the mask. Therefore, latency must be carefully controlled for the target bandwidth to avoid such scenario. Now that we have understood the impact of ISI, let's find ways to mitigate them. These techniques are collectively known as equalization that can improve both voltage margin and timing margin. Let's start with the simplest one, known as pre-distortion. Given we have already seen what happens when we send a narrow pulse, it spreads out at the receiver side and creates a positive residue before and after. To mitigate that, intuitively we can distort them in the negative direction before the pulse and after the pulse, such that after dispersion my ISI component will become 0 or close to 0. Because this involves 3 pulses over 3 UI, I need to take the symbol and delay it by 3 delay elements and sum them up with a weighting factor. This structure is readily available by breaking the transmit signal swing into 3 segments. From frequency domain viewpoint, we are effectively flattening the frequency response, but this is done by dropping the DC. This happens because at the transmitter side we are transmit swing limited. Therefore, including the conceptual negative pulse, the peak-to-peak swing has to remain the same. This swing reduction is also visible in the eye diagram. We see that the peak signal swing from 400 mV has dropped down to 200 mV. Nevertheless, if we look at how much ISI distortion we had in the eye diagram, that has significantly reduced, and so did the transition data dependent jitter. However, extending this technique to higher data rate can be challenging because to compensate higher loss, we are further reducing the DC component to flatten it out, and as a result, my eye amplitude keeps reducing. Therefore, an alternative approach could be peaking, equalizer, or CTLE. This is where we provide high frequency gain with an amplifier, but we intentionally reduce its DC gain to create high frequency boost. This can be done by simply creating a 0 and 2 pole in the transfer function. If the 0 comes before the pole frequencies, then it is expected that such boost behavior will be visible. It can be implemented with a simple differential amplifier where we put a degeneration resistance in the source. Therefore, my transconductance will be reduced at DC. However, at high frequency, I put a bypass capacitor. Therefore, this degeneration disappears and we see the full transconductance of the devices and my gain is restored. Using such approach, we can see that we are still flattening the frequency response, but now we have high frequency gain. Therefore, my eye opening significantly improves. Going beyond these linear approaches, we can also do nonlinear equalization in the form of a decision feedback. Here, we first make the decision, and based on those decisions, its residue ISIs are corrected using this delay element to reach out the different post-cursor values. For example, assume this red dotted line is showing the unequalized pulse which had significant post-cursor ISI. But after the correction, the blue one shows that all ISI components are forced to 0. Note that because it requires the decision and only then it corrected, it cannot correct any ISI that appears before that, meaning precursor. Looking at the eye diagram, we notice significant discontinuity. This happens because input of the summer node is a spread out pulse, whereas what we are correcting after decision are UI wide pulses with sharp edges. Yes, therefore their summation would show these discontinuities. However, at the middle where it matters in terms of voltage margin, we see significant improvement. Now it's a good point to summarize this equalization technique. From the left to the right, equalization complexity increases and there increases the performance. We are running the link at a higher speed from 10 gigabit all the way to 20 gigabit. But despite running at high speed compensating more loss, the voltage margin improves and so does the timing margin. When I move from analog to digital domain, the fundamental equalization concepts remain the same. What will change is the implementation method that we will discuss later. Now that we have covered the background on equalization and timing recovery, let's see how these techniques evolve to the analog to digital domain. Let's start with the timing recovery. So CDR is based on PLL, and these techniques are very well understood at this point. Their implementation is also evolved and matured, so that is also well known. Here I will simply point out some of the limitations that we are facing today in FinFET type technology. First of all, the reduced supply voltage is making the designing a charge pump a lot more complicated. The loop filter takes significant area and does not scale well. Finally, the VCO has its supply sensitivity and its own random noise generation that requires careful filtering. So when we move to the digital domain, we can start with this charge pump and loop filter. This can simply be represented with an accumulator, its a scaling factor, and a proportional path, then goes to an adder. Obviously, this would be digitally synthesized, therefore at a lower clock rate. That mandates a decimation block or a majority voter ahead of it. On the VCO side, we can represent it with a digital accumulator and a digital to phase converter. Because the accumulation is in digital domain, therefore it's noise free. So the random noise accumulation no longer takes place. For those who are not familiar with digital to phase converter, here is a short summary. It basically involves an accumulator followed by a phase mixer. Phase mixer is essentially two diff pair where the drains are shorted. Therefore, if I give an input clock as an in-phase clock and a quadrature clock, then I can generate any vector in between. Such clocks can be generated from a PLL. A ring oscillator can easily provide in-phase and quadrature clock, for example. So, when we mix these two phases with a weighting factor, I can generate any vector in between, essentially any phase in between. Not just that, when we sequentially rotate the phase in a particular direction, we notice that compared to the input clock slope, we can generate a different slope, which effectively translate to a frequency offset that can be used to compensate any frequency offset between transmit data and recovered clock. So now that we understood the techniques, here we want to generate a comparative picture. Therefore, I picked two analog CDRs here along with the digital CDR. For fair comparison, I pick comparable data rates. So the first thing that pops out here is the large loop filter, and here is the synthesized small loop filter. So as expected, there is a significant area improvement. Not just that, there is also a significant power improvement. On average, we have seen in literature about 10x improvement in power and area is achievable with digital CDR. But performance should also be considered. Notice that due to digital synthesis, loop filter has latency, therefore the bandwidth may significantly drop. We may have lower jitter tolerance and limited frequency offset tracking. However, as the technology is scaling, and synthesizable clock rate is improving, and we can have much higher bandwidth. And also using fraction techniques, we can compensate significant frequency offset. Now let's see why and how analog equalization moves to digital domain. Here is our state-of-the-art analog equalization strategy, but let me point out some of its limitations. Starting from the transmitter side, the transmitter segments and delay elements are fixed. That means in terms of modulation and number of equalization taps, we have no flexibility. On the receiver side, CTLE is limited with its gain bandwidth, and that is not scaling well in terms of analog performance. We do have digital equalization in the form of DFE, but the sum nodes limited bandwidth, linearity, and this loop latency maintenance is becoming more challenging. In addition to these challenges, we also see a trend moving towards multi-level signaling. Since in an energy case, I have only 2 levels, therefore only 1 bit can be sent. The only way to improve the speed is shrink this UI. And that's when we move towards higher frequency where we have to deal with channel loss and discontinuity. Instead, we can take this 2-bit information of 2 UI and map them to 4 level. In this case, I widen the UI. That means I can stay within less lossy part of the channel. By doing so, now I need to compensate 16 dB less loss. But I have these 4 levels, which means my eye height has now shrunk by 1/3, which is 9 dB SNR penalty. However, it's often argued that this 16 dB equalization benefits overshadows this 9 dB SNR penalty. But this has to be understood more closely in terms of eyesight. Therefore, we create a simplistic case like slide 9 with a one-tap post-cursor eyesight. In the case of NRG, it is +1 and -1 symbol levels split by 2 levels in the presence of H1. But in the case of PAM4, each of these levels is split to 4 levels because previous symbol can have any of these 4 levels. As a result, we see the constellation point difference has now shrunk significantly, which means my eye opening is reduced. Not just that, even if we consider the symmetric transitions in this case, the spread out of the zero crossing indicates much higher data dependent jitter. Together we can say residual ISI would impact me 3 times more compared to energy in PAM4 case. To understand this scenario, let's consider a practical case where we are sending 112 gigabit per second from the transmitter side in PAM4. Therefore, at 28 GHz, we need to compensate about 38 dB loss. With such high loss, my single bit response is severely dispersed, that is shown with significant precursor and post-cursor ISI. However, we can deploy this analog equalization technique. From the TXFIR, I can have about 8 dB loss compensation, and CTLE can provide residue ISI cancellation, which flattens out the frequency response like this green curve shows. In time domain, we see this equalized single bit response with the red one where things are brought down to 1 tap, but we have a bit of residue ISI in precursor and in post-cursor. Let's see how this residue ISI impact us. In case of energy, if I generate the eye from this red single bit response, I do see significant opening. But when it comes to PAM4, there is no eye opening. And this can be attributed to the 3x ISI penalty that we have previously talked about. So how do we deal with this residue ISI? In ADC DSP case, we can first digitize it, and then in DSP we can implement a FFE. Here is this FFE response that can take this partially equalized eye and clean up this residue ISI nicely to a single tap where no precursor and post-cursor ISI are visible within the linear scale. As a result, we can see a significant eye-opening improvement. To get an insight why CTLE cannot provide such response, we can convert this FFE into its frequency response. And from this frequency response, it's evident that such frequency response will require many poles and zeros and precise location of those poles and zeros that is nearly impossible to do in analog domain. In addition to that, we also see one more trend in recent data converters. If we plot the Nyquist frequency or the sampling frequency in the x-axis and we plot their figure of merit in y-axis, we see the recent published ADCs has shown significant performance benefit. These two factors together leads to a scenario where at high data rate, when I have to compensate very high channel loss, ADC DSP solutions not only outperform an analog solution, and that is the only solution that is viable at that speed. If we look at our traditional analog transmitter implementation, we have the transmitter segmented in different number of elements, and we have also the number of delay elements set by the taps we need to equalize. Reconfiguring this means we have to have arbitrary number of these high-speed delay elements and also the segment, which is an expensive proposition. Instead, we can transfer this entire structure to the backend before serialization, where things are a lot more affordable. Let's see an example. Here we have a 7-bit DAC, and we will be using that to send a PAM4 data stream. The 2 bits of the PAM symbol can be used to choose one of these 4 7-bit values from the transmitter side. So these 4 values then maps to this PAM4i. Notice that we can make this I bigger or smaller depending on the 7-bit values that we have in the entry in a simple way. Now let's add some equalization to this. So to add the equalization, we have another 8-bit lookup table from which we can select a particular 8-bit value, such that after addition we create these 16 levels, where each of these levels are split into 4 levels. As a result, we get this pre-emphasized I from the transmitter side. Notice that these 8-bit values can be generated from any arbitrary number of taps and with arbitrary magnitude. As long as they map within the 8-bit, it should be sufficient. Similarly, for pre-emphasis, we can do another lookup table from where these 8-bit values are added to the main and the post cursor. Therefore, we can have, using this 7-bit DAC, arbitrary number of precursor taps and post cursor taps and create this pre-distorted I. The only limitation here is the 7-bit value number, which means that these blue elements can at maximum be only 128. In addition to that, we can also shift it around, move it up or down depending on the common mode that is needed by the application. Now let's see some of the examples. Here is a 7nm DSP DAC implementation consuming only 15 milliwatt and very small area here. It can provide such flexibility. It can provide large signal swing, energy modulation, as well as PAM4 modulation at different data rates. We see such architectures scale beyond 200 gigabit per second, but even at such a speed, the DSP DAC part does not consume significant power. It's mostly on the clock distribution and in serialization. Perhaps the bigger impact of DSP DAC is the flexibility it provides. As shown in this work, it can not only send different level of PAM modulation, advanced modulation such as OFDM is also doable with such flexible architecture. If we follow the signal path from the transmitter side, we first see that the signal is partially equalized or de-emphasized. And then at the receiver input, the eye is completely closed, and even after the CTLE, the eye remains closed, indicating that bulk of the equalization would be done at the DSP using FFE. However, partial equalization is needed for 2 reasons. First, given the channel does not attenuate DC, some amount of DC reduction would be needed so that the signal at the receiver side fits within the linear dynamic range of the receiver. The same rationale is applicable for the CTLE too. It needs to bring the signal within 400 to 600 millivolt depending on the ADC's configuration to meet its dynamic range. In addition to that, it partially helps meeting the SNR budget at the decision point. Since most of the equalization would be done using FFE, let's take a closer look at it. So this is the pulse response that has, in addition to the main, significant pre and post cursor ISI. Our objective using the FFE is to bring this to a single tap response without any pre or post cursors in that pulse. One of the ways we can do it, we can delay this pulse and then subtract it such that the main aligns to the post cursor, and then it would be significantly reduced. And similar approach we can do that for the precursor. We can shift the pulse so that the main aligns to the precursor and significantly reduced. To keep the system causal, we would add delay to the main rather than trying to go ahead of time and to cancel the precursor. More importantly, we see that the spread out pulse will also have its residue before it. That means we need to continue the process further to completely clean up the any residue tail both on the precursor and the post cursor side. Ultimately, we will receive a pulse that is limited to a single tap, but the main will be significantly reduced. This happens because again, as we see, it's a spread out pulse. Means when I was subtracting the post cursor, some amount of precursor was there that was pulling down my main, and the same happened when I was cancelling the precursor. So this reduction in the main can also be viewed as a signal power reduction or SNR degradation that will be discussed further later on. But now let's focus on the hardware implementation. First, we digitize it to an n-bit number, and then we delay that to create these replica pulses as we need, and then we scale them, and the summation happens, which with polarity could be both subtraction and addition, and so that we get a 2n-bit of equalized output. Let's look at it first, the digitization process. At this speed, we obviously have to go with Nyquist ADCs, and our options are SAR ADC or sub-ranging or pipeline. Going beyond this in terms of detail of that implementation is not within the scope of this tutorial. But I would encourage you to look into these references if you want to know more about this ADC implementation. The most important thing that I would like to point out that these ADCs are gonna be a time interleaved. Means each ADC works at, for example, 875 megahertz, and we will have 64 of them to achieve the 56 gigasample per second rate that we need. And this has an implication in our equalizer. Imagine we have an unequalized single bit response, and it is digitized using these ADCs. And now each ADC is going to equalize each of these red dots, meaning at the ADC output we have readily available both the main pulses and all the ISI components. In other words, if we can use those delayed version of the data, we can get the equalization done by combining the main and subtracting the ISI components. However, to do that, we need to bring things in the same cycle. That's why a 875 megahertz retimer is used in most cases to bring them on the same cycle. And once they are within the same cycle, then we can simply scale them and combine them according to this FIR equation so that equalized output is available here. In a way, from the left side and the bottom side, we can think this is a multiple input and multiple output system. So now that we understood the way it is implemented, let's look at where the noise sources are in this receiver so that we can get a better handle of the SNR of the system. So obviously we will have some input referred noise of the CTLE. We will have clock jitter that samples the data. We will have ADC's input referred noise, and then quantization noise. Now all of them are going to be shaped by the transfer function within their path. So to meet the SNR, one of the objectives could be minimizing these noise sources, but that's not always possible because of the many hardware power related constraints that we live within. Therefore, the other factors we can minimize is the transfer gain, and the one that comes at the very end, the FFE, is kind of the knob that amplifies all the noise sources. Therefore, it's worth looking into how can we minimize the FFE's noise amplification. Thinking of if we have a sinusoid as my input signal, let's look at the SNDR at the ADC output. So we'll have the sinusoid at this frequency in its peak, and we'll also have the noise flow defined by this red line from the FFT of the signal. Once it goes through this FFE process, it's going to shape the spectrum. And due to that, you can see the signal has dropped and the noise floor on this part has enhanced, meaning that at this output it will be difficult to even maintain the n-bit SNDR requirement as it was available at the output of the ADC. Which means that although I am doing the computation of the FFE, I have a 2n-bit resolution, my ultimate resolution is already set by n-bit or even lower than that. So in such scenario, how can I maintain my resolution? One of the ways we could do it conceptually is to bring the equalization before the quantization process happens and then do the quantization. In this case, I will be able to retain my 2n-bit resolution. This may indicate that I am suggesting moving the equalization in analog domain before ADC, but actually not. We can take this concept and somehow try to fit in within our digital implementation. This is one way of doing it. Think that we have some sort of a calibration, offline calibration cycle such that we can generate the FFE outputs with a higher resolution, and then we store them in a lookup table. From the regular path, we actually use the FFE output as a address decoder, and using that address decoder we can pick up one of the values from the lookup table. Because these entries are made with a higher resolution, even the selected value will retain that resolution. That's one way. Even using a 5-bit ADC, we can select an output which has a 9-bit resolution. Now this should not be violating in the basic understanding of our ADCs. It's not that we are effectively bypassing the resolution requirement. What this basically means that statistically speaking, if we have 2 to the m number of possible outputs, we are selecting a subset of 2 to the n. And these 2 to the n's are statistically most likely outcomes as seen from these distributions. This does not eliminate the worst case quantization noise. It only limits the probability of it happening. Because in this system we are targeting only BER of 10 to the minus 6, even such a statistical improvement can become beneficial. And this implementation also reduces the power and the noise impact. However, such techniques should be limited to only pre and post cursor tabs because of the complexity of the lookup table and the number of entries that goes into it. The remaining tabs can be done in a conventional manner because of their magnitude is smaller. The noise amplification should not be that significant, and you can still see the eye improves. Lookup table based approach does have some limitation. Regular computation can be easily synthesized and fits within the area budget. But once we create the lookup table, we need to store them in SRAM and the area can improve. However, such penalties can significantly reduce as we go to below 10 nanometer. Both power and area of computation and storage improves. Now we will shift our focus and look into some of the power reduction techniques. We notice that in a large ASIC there are different type of channels. Some of them has much lower loss. For those lower loss cases, as this work has shown, by simplifying the equalization as well as sometimes reducing the ADC resolution can significantly improve the power consumption. The ADC resolution reduction is much more applicable for the SAR ADCs, as shown in this work. When we run in 7-bit mode, we require 7 to 8 cycles, because including redundancy, because on each conversion cycle 1 bit is generated. But when we are running at a lower resolution, after 3 cycles we can pause the signal or the conversion cycle, and this way we can save significant power. From 225 milliwatt to reduction to 64 milliwatt is significant in most applications. In addition to that, opportunistic power savings are also possible in ADC DSP solution. The one that shown in here explains that reliable zeros and reliable ones are often available, such that we can completely bypass the equalization process and save the power associated with those bit detections. Now we shift our focus to the decision feedback equalization. The core concept of DFE is already discussed previously. Here we will see one implementation limitation. The decision created at the comparator output goes back to subtract its ISI. Therefore, this loop includes both a strong arm and the summer node has to be less than 1 UI. But notice that the strong arm's decision time can vary quite a bit depending on its input signal. For example, it can, in a 65 nanometer, it can go from 100 picosecond down to 60 picosecond. With such variation of the input signal, it will be difficult to fit within this time constraint. Instead, what we do here is we use a speculative decision method. Notice that if the first post cursor is unequalized, then instead of H0, we create two levels, H0 plus H1 and H0 minus H1. Right? In a direct feedback equalizer, we would have subtracted this H1. Here, instead, we are adjusting the threshold. By lowering the threshold from 0 to minus H1, we can still retain my H0 margin. Therefore, we make two decisions with these shifted thresholds ahead of time, and then within the loop, based on the previous decision, we select only one of them. Therefore, I can retain my H0 margin, and at the same time I can take this strong arms variable delay out of this feedback loop. So in this case, a D flip-flop plus mux and their latency to limit within 1 UI is much simpler. However, this requires two comparators instead of one. This increase of the comparator actually is an exponential term. In general, n-tap DFE, it's L-1 and L to the n number of comparators are needed. So it is much easier to implement for energy, but as we are moving to PAM4, we see this exponential increase, which makes it difficult. Why this exponential increase comes from, we can explain it for the PAM4 case. Usual PAM4 requires 3 thresholds. Imagine 0 at plus 2 over 3 and minus 2 over 3. What happens in a case of loop unrolled is that each of these thresholds are going to see 4 possibilities of the previous symbol. Therefore, these 3 is multiplied by 4 and creates these 12 thresholds. The same concept scales to the digital implementation. In a time interleaved structure where we have 32 time interleaved paths, after FFE, we are bringing things to 2-tap, main and 1 post, and then we create these subtractors which are equivalent to the comparators in analog domain, and then we create the symbols and select between them. Instead of 12, in this case, due to the 32 time interleaved path, we have equivalent number of mux and flip-flop in this delay. Now that we understood the basics of the digital architecture, let's see some of the limitations, where it comes from, and how can we overcome them. So for timing recovery, we do have two options. The first option is that we can use our data samples, and we target that equalized samples should concentrate around this constellation point, which can be defined as D11. So any error from this uh, plane can be considered as a error, sample minus D11. And we also look into the slope of the signal. So at this point where the slope becomes 0 and deviation from D11 becomes 0 is my log point. Relative to that, A and C would be considered earlier and B and D can be considered later. Since we are using a single clock phase that would be decoded for both data and for timing recovery, there is benefit to such approach from clocking point of view. However, when we look at the slope of the signal, the slope is at its minimum in the log point. Therefore, it will also provide minimum gain. Instead, if we sample at the transition, then we can define delay as the 0. And similar to previous case, deviation from the delay is considered as error, and the slope of the signal can be attached to that to calculate the early late decisions, as for example A and C would be considered early, B and D can be considered late for the edge clock perspective. Because we are sampling to the edge, we also need additional clock phase to decode the data. This additional requirement of clock phase makes it less attractive, but the slope is at its maximum. That means it can provide high phase detector gain. Either approach we accommodate, and this is what the structure with ADC DSP solution looks like. Note that after we digitize, we move into sub-red clock, which most of the time is synthesized at 875 megahertz in 16 or 10 nanometer nodes. Then we actually go through an equalization before we can do the phase detection. This is necessary because at the sampling point, as explained before, even after CTLE, we have significant ISI left and the eye is closed. All these algorithms are developed based on an equalized eye, but with a predefined delay which has nicely converged. Therefore, an equalization would be necessary ahead of the phase detector to provide sufficiently accurate results. And this is where the trade-off between latency and tracking bandwidth generates. Because everything is synthesized in 875 megahertz, this equalization will accommodate significant latency in the feedback path. Therefore, the ISI and latency is the main difficulty in this problem. Let's see a breakdown of this latency in this particular implementation. ADC itself will require at least 2 cycles because at the sample and hold, and then in the asynchronous SAR we need to bring things into synchronized domain. Right? And in the digital FFE there will be at least 3 parallel cycles to do the multiplication, addition, and including the pre-taps. And the phase detection can be done in 1 parallel cycle, but the accumulation, proportional path addition, and the further accumulator to drive the PI, everything needs at least 2 cycles. In total, it's 8 parallel cycles, but the parallel cycles are at 875 megahertz that translate to 256 UI. With this much latency in place, what we see is significant limit cycle dithering there. To imagine how latency causes dithering, you can imagine that the phase is a bit ahead of the target phase, therefore the clock is earlier. But this early information does not propagate through this loop fast enough. So the loop is still keep on deviating, and by the time the early information reaches, it is quite far away from the target phase. And then the loop realizes it's early and then it slows down. And similarly, the late information also takes a while to understand that it is overshooting. Therefore, this limit cycle behavior happens with such large loop latency. What this causes is due to this additional noise at this given frequency, it dips in the jitter tolerance plot and violates the margin. One simple way to overcome this without reducing the latency would be reduction in the proportional gain. Therefore, we see in the green plot the dithering is only to couple of cycles. But such reduction also reduces the bandwidth, as we can see from this plot that it takes much longer to settle around the target. This reduction in bandwidth means in the jitter tolerance we shift towards the left. So although we avoid the dip, but we still violate the timing margin and jitter tolerance. Now let's find a way how can we avoid this latency issue. We recognize that there is a unique difference between the data detection and the timing recovery. And the data detection requires every bit to be detected correctly to achieve BER of 10 to the minus 6. But timing recovery needs to be only on average be logged. Therefore, the data samples and the PD decisions accuracy can be somewhat sacrificed. Which means I can simplify the equalization to a much fewer number of taps to get rid of some of the cycle delays such that the timing recovery can fit within the target, whereas the data recovery can use its full-blown equalization, many number of FFE taps and DFE such that the decision can be detected with the highest precision. In addition to that, this MMPD can actually minimize the dithering around the delay, which also helps the adaptation. Such approach was presented last year at ISSCC, where it clearly shows that the timing recovery path is the bottom one and the data recovery path is the top one are isolated. Decoupling them allowed them to reduce couple of cycles, so they achieved 4 MHz. But decoupling had other advantage such that the data recovery path can use 22 tap FFE, 7 tap floating FFE and 1 tap DFE, which allowed them to compensate much higher loss. Now, in option 2, we can take this to one step further, knowing that we are already splitting the timing recovery path and the data recovery. One relevant question to ask is ADC the right way to view the timing noise? Although timing error can be inferred from there, but if we instead use a time to digital converter or quantize the phase, then we can directly use that to close the timing recovery loop. In this case, the latency can be reduced drastically. For example, TDC takes one cycle, phase detector takes another, and loop filter is another. So in reducing that to only 96, CUI can significantly improve the jitter tolerance. But we need one extra phase, but more importantly, the I at the TDC input still has significant ISI that it needs to handle. So it's worth to look into how ISI makes my timing recovery challenging. For example, we took this ISI limited case for NRZ. Here we can see that significant ISI not only closed the eye, but it really made the zero crossing distribution and dispersive. In fact, this dual distribution would make the timing recovery quite challenging. But we take this one step further and decompose this zero crossing distribution to each individual pattern that contributes to it. For example, 1010 and 0101 patterns created the left peak of the distribution. Similarly, 1101 and 0010, these two black traces create the right peak of the distribution, and they both are ISI impacted. In between 1100 and 0011, this blue one would be a better lock point, but due to these ISI impacted distributions, it's smeared out, and actually we see the lock probability both left and right and very little gain in the middle of it. So how do we improve such scenario? One easy way to do that is to say that I have to avoid the zero crossings of the ISI affected pattern. Rather, instead of using the E naught, I use E plus 1 and E minus 1, shifted threshold in the edge. My objective is to actually intercept the black and the red traces intercept points such that all these zero crossing distributions are aligned to each other and I can get a much better phase detector gain. So E plus 1 and E minus 1 can be appropriately adjusted to do so, but we also need to find a way to differentiate the black pattern from the red one. That can be done using the data samples D1 to D minus 1 that are readily available at the ADC output. And finally, having the edge thresholds actually allows me to quantize the phase error with higher resolution, which means I not only get early or late information, I get earlier or later information. This multi-bit output has several benefits. But let's first see how this D plus 1 and D minus 1 can help the situation. It is more or less motivated by pattern filtering. In a very ISI limited pattern, we can see the zero crossings actually are distributed across the UI, which can make timing recovery quite challenging. But if we set these two thresholds such that only the zero crossings that are where the symbols varies from above this level to lower these levels are considered, then we get a much tighter distribution, and we can further tighten this distribution by widening this. And so this actually, similar to pattern filtering, is an effective way to pull out the ISI free transitions which can be processed to achieve faster loop bandwidth. Such techniques are already implemented, are in place. Most of the time though, this has to be adapted, both the edge crossings and the data threshold, such that we can tighten the distributions. This work has demonstrated three main benefits of TDC-based approach. First, because we are quantizing the phase error with higher resolution, in-band phase noise reduces. In this case, we can see 6 dB improvement in the in-band phase noise. Second, by linearizing the PD with multiple bits, and the tracking bandwidth variation over input jitter also reduces, as it shows here, 3x reduction. And finally, the jitter tolerance also improves. Such techniques are also applicable at high speed as adopted in this 112 gig SerDes running with 56 gigasample per second ADC. Because at such high speed, phase resolution is difficult to achieve. That's why the PI is included inside the PLL loop by adjusting, by putting the phase interpolator in the feedback path of the PLL. However, the more important point is the additional power consumed in the TDC and the processing associated with it. It turns out that burning only 20 milliwatt, it can implement the TDC in a power and area efficient method, which is only 10% overhead. The performance benefits are significant. It achieves the jitter tolerance over different data rates over different standards. And also, to compare with the MMPD, this can provide much higher gain because it's sampling at the edge where the slope is maximum. In the last few slides, we have seen how latency related limitations can be overcome in the digital implementation. Although it also addresses ISI partially, there is a bigger limitation ISI related in our equalization that requires advanced equalization. Being in digital domain, there are few advancements that we can make to improve that and achieve better SNR. Next, we will discuss those. Let's first think of what happens in an FFE only equalization. And the digital implementation provides us the flexibility such that after equalizing them to a single tap, we can actually compare the signal to noise ratio to the symbol error rate. And from the measurements we see that at the decision point our signal to noise ratio correlates very well to the theoretical expected values. But if we walk back from the FFE output towards the FFE input, we see a shift in this SNR versus BER curve that indicates that the SNR that is required at the input of the FFE is higher compared to the output to achieve the same BER. In other words, FFE is significantly degrading the SNR of the system. To understand why it does it intuitively, we can look at the single bit response. So this red one was before equalization, and after FFE equalization it has nicely brought it to a single tap as expected, but its amplitude has significantly dropped, and that drop is basically indicating the degradation in SNR. Let's explain this point further. Here the same single bit response is shown with the precursor and postcursor amount explicitly. As we discussed in slide 55, that once the FFE tries to equalize with the single bit response, there is a significant reduction of the main amplitude. And this reduction in the main magnitude is also visible in the frequency response from the FFE transfer curve. We see that at low frequency it is significantly attenuated, and at high frequency it goes to 0 dB. For fair comparison purpose, here we are normalizing all the plots to 0 dB at high frequency. And this will ensure the high frequency noise is more or less same amount in between different equalization approaches. Now this reduction in the low frequency magnitude relates to the reduction in the signal magnitude, and therefore my signal to noise ratio has degraded. If we move away from FFE and go to one tap DFE plus FFE combination, then I can reduce this reduction and recover some of my signal power. I can do that more effectively if I say that I will leave with some amount of precursor and some amount of postcursor, and of course with the main. In that case, we can see that from the transient viewpoint my signal attenuation is much less, and also is indicated the same in the frequency response. So there is an opportunity to recover this SNR degradation associated with FFE if we are able to somehow live with these ISI components. So we need to find out that how can we make correct decision in the presence of ISI. So the example we take is the similar one. We have one precursor main and one postcursor, and for simplicity the transmission system is still energy. That means from this received signal, each of these red dots reflective of one transmitted bit. However, because of the ISI in the system, each of these red dot is a resultant of not just its current transmitted bit, its combination of the previous current and the next transmitted bit, as indicated by its precursor tap, main tap and post tap. Therefore, we should map these received sample points to the expected levels. Expected levels are effectively in the three transmitted bits convolved with this channel response. Here in this case, we will refer to them as constellation points. If we were only limited by 3 ISI and there were no noise, then each of these red dots would have landed on top of those blue lines or ideal constellation points. But because of the noise, they are deviated from their ideal constellation. For example, in this case, they are in the middle of it. But we can still say that
closer these red dots to their constellation points, more likely they are belonging to that sequence. For example, this red dot here is most likely to be 0, 1, 1, and this bit is actually 1. But not always these constellation points and the received samples will be so close to each other. For example, here when this red dot is sitting in the middle of these two dots, it is difficult to say which sequence this red dot belongs to. We can eliminate the further ones, but these two closest ones are hard to be eliminated. In this case, therefore, we extend our probability calculation part. Instead of just looking into these two distances, we try to see what is happening over the sequence. Meaning, all the possibilities that crosses through this particular constellation will be considered. This leads us to these three possibilities. Each of these possibilities are indicated with the lines in the graphical picture. As we see that when we extend our observation horizon beyond this symbol point, the brown line deviates from what actually it took place, and the red one also deviates further away from in this black line, indicating that in the overall picture these two are less likely to happen, and only survivor one is the black one. And this observation can be mathematically mapped over here. So first we calculate the expected level, or ij hat, and then we calculate the likelihood by calculating this distance. And then we not only just look at the distance in one sampling point, we accumulate these distances over an entire sequence. And after accumulating that distance, then we find the most minimum one, or the survivor path. From hardware point of view, first we digitize, then we calculate the branch metric. Branch metrics are nothing but the calculation of this likelihood. And then we accumulate these branch matrices and then compare and select the most likely one, or the one that overall achieves the minimum distance from their constellation points. Therefore, this is a computationally intense process. Most of the time translated to higher power consumption in earlier work, but some recent work has shown that the power consumption can be significantly reduced below 150 milliwatt, or even in some cases down to less than 100 milliwatt. But it should be noted that such power consumption was achieved by sacrificing in the full-blown implementation to a simplified one. Here, for example, RSSD stands for Reduced Step Sequence Decoding. And the second important point, it has to be implemented in a process such as 10 nanometer or lower, so that the digital implementation translates to lower power consumption and less area. So it's important to understand the computational complexity and where it comes from. So it starts with the number of states. That is defined by two things. One is the possible symbols. For energy, there are two levels, 0 and 1. And then channel memory, which is the number of taps, basically the number of precursor and post-cursor taps we are including into the Viterbi algorithm. And finally, the trellis length, over which we will accumulate those branch matrices or the probability factors. And then the branch matrix calculation involves both the trellis length and number of states. So there are several techniques used to reduce this, because A is not often in our hand. For example, if we are with PAM4, as most of the standards has moved to, we cannot do much about it, but we can reduce the channel memory having a FFE to reduce the number of taps. Similarly, DDFSE also get rid of the post taps through decision feedback equalization. And there are some set partition techniques that can be used to further reduce the number of states that are considered here. And two important techniques that in recent years has taken significant attention is 1+D, and another method is analog to sequence conversion. So remembering how the hardware would look like, I would have a to D, and then we move to branch metric calculation, where we actually calculate the probability of the received sample belonging to a sequence. We can combine these two parts together to something called analog to sequence, where the received sample will be mapped to a digital outcome, but this digital outcome will not be in a traditional sense a signal space, a digital value, rather in a time sequence of bits. Let me elaborate this a bit more clearly. For example, when I received a sample at time t3 here, this sample is mapped to this expected value or the constellation point 011. This 011 does not indicate 3, rather it indicates that my previous bit was 0, my current bit is 1, and my next bit is going to be also 1. In this way, I can not only decode the nearest sequence, or we can decode nearest two sequences, for example in this case, and we can also calculate how likely they are to be belonging to that sequence. Recent implementation such as these two has shown that the power consumption can be significantly reduced if we implement in this way. For example, 35 milliwatt for 10 gigabit or 82 milliwatt for 28 gigabit is pretty much ballpark compared to what the traditional SerDes are achieving. However, we need to extend this concept further to decode the trellis, and that's where 1+D can provide some improvement. Think of that we have created a 3-bit trellis as an example for simplicity. This involves the current MSB, current LSB, and only one bit from previous symbol, which is LSB. Because 3 bits can combine in 8 possible ways, those are shown here. Instead of 8 levels, because of 1+D, which means my current symbol and my previous symbol are of the same magnitude, these 8 levels converges to 5 levels. This reduces the number of comparisons I need to do to decode these levels. I can take this one step further, where I can redistribute the weight between MSB and LSB such that the number of levels in this case is decoded down to only 4. Now these levels by themselves do not decode the sequence or the symbol, as each of them can be translated to multiple number of trellises. That is where the trellis decoding is needed. So imagine we received a signal with the red dots corresponding to each received sample. Now each received sample is first decoded back to the levels +1 to -3 based on these 3 thresholds. Notice that the benefit of 1+D encoding is that it starts and ends with a fixed trellis. Therefore, my trellis length L can be significantly reduced. Next, we map each of these received level to the possible trellises, and then we take each of these current symbol and compare to the next previous symbol, such that we keep only 2 out of the 3 possible paths. And finally, we reverse the relationship such that the sequences are converged to a single survivor, and that's how the trellis decoding is done. The advantage of doing it in this way that it's a bitwise comparison, so using only XOR gate and a mux selection, I can decode both the accumulation comparison and selection part to a single bit comparison, and the hardware is significantly simplified. Comparing this 93 milliwatt at 32 gigabit per second compared to the traditional implementation of Viterbi decoder is a much simpler alternative. This brings us to the end of this tutorial. First, note that equalization is an evolving process, so we have to pick the right solution space and the right technology to justify that. Precise ISI cancellation is needed for multi-level signaling. And also, a DSP-based architecture should be adopted in a technology where it is DSP friendly. Therefore, highly scaled technology nodes less than 10 nanometer and multi-level signaling is the right solution space for ADC DSP. ISI cancellation in general is easier to understand, implement, but it has SNR penalty. Therefore, ISI assisted detection technique is more suitable from SNR point of view, but its complexity must be reduced, and that's where the future of equalization is progressing. I would like to point out two talks this year's ISSCC that covers the material related to this tutorial. I hope you can make time to view these talks. And here are the list of references for your future reading on this topic. Thank you for joining this tutorial. I hope you enjoyed it. I will see you at ISSCC.